probability and some complex analysis. We'll try to introduce everything you have known, at least in some expository form. So please just mark in these forms what you know, what you don't know, and we'll just spend the time accordingly during the first 4, 5, 6 lectures.
Mm-hmm. And if you finished, if you can just let Dimitri know, and he can collect the. He's at the back, so yeah.
To the assistant, and we'll try just in real time to tabulate the answers to see how we proceed the second hour.
You didn't get one. Dimitri, do we have another form? Yeah.
So there are no exercises today. We'll start today with 1 hour sort of expository thing where we'll show a lot of pictures and say some words. And then we'll proceed to the background and complex analysis, which will proceed depending on how you fill these forms. So, and the first, yeah, off we go.
Okay, so welcome to this this module on random growth and Loewner evolution. So I'm Amanda Turner, and I'll start by just giving you an overview about the random growth element of the course, what random growth is, why we care about it, and what some of the interesting mathematical problems are surrounding random growth. And then after that, Smirnov will take over and talk a little bit about the Loewner evolution as aspects of the course. Okay, so what are random growth processes? Well, essentially the picture to have in your mind is a cluster of something like cells or molecules that essentially grows by new cells or molecules being attached to the cluster one at a time according to some kind of stochastic rule. And these kind of things occur widely in nature. We'll see some examples in a minute. And the precise physical mechanisms by which the growth occurs determines the stochastic rule for attachment, which then results in potentially very, very different clusters. So here's a simple example. So what we have in this picture is just a lichen growing on a rock. And how did it grow? Well, you started off with some cells, and they gradually sort of reproduced to get this cluster. And so each reproductive event results in a new particle being attached to the cluster. And in this particular case, where is the next particle going to occur? Well, we don't know. This is why it's a random process. But it's going to be somewhere along the cluster boundary. Somewhere along this boundary is going to be a reproductive event resulting in the next, in the cluster getting bigger, acquiring an extra particle. And it's going to be roughly equally likely along this boundary. Any of the particles along this boundary could reproduce, and that will give you the next one. And so what you get, if you look at the sort of shape, is kind of what you would expect, really. It's approximately round. There's no direction that sort of is any better than any other direction for the growth, and so that the whole cluster just sort of grows roughly round, but with some sort of fluctuations on the edge, sort of corresponding to the randomness in the system. Here's another similar picture. So this is actually Sir Alexander Fleming's penicillin sample, and again the same thing happens. You start with some penicillin at the origin, and the mold gradually sort of reproduces to grow this cluster. And as before, the next particle can arise anywhere along the cluster boundary. And again, as before, we get a very, very similar shape. So it's roughly round, but with some sort of random fluctuations around the boundary. So this is the sort of classical biological growth mechanism by which we get these random growth clusters. But they don't just occur in biology. So here's an example of mineral deposition. So what's going on in this picture is we have an electrode in a solution of copper sulfate. And in this case, copper ions diffuse through the solution until either they'll hit the electrode or they'll hit some point of the cluster, at which point they stick. And again, we have a very, very similar situation to before, in that we have some sort of cluster and it's growing by successive attachment of particles, But in this case, the rule is different. So before the rule was a reproductive rule. So any particle had an equal chance of, on the edge of the cluster, had an equal chance of reproducing. This time the rule is, well, where is a diffusing particle going to hit? And it's no longer the case that anywhere along the boundary is equally likely. In this case, if you imagine a diffusing particle, it's going to find it quite hard to make it all the way into here. It's much more likely to hit one of these tips on the way in. And so you find, in this case, you get these deep fjords growing where growth is very unlikely to happen. Meanwhile, on the tips of the particles, which are sort of sticking out into the solution, diffusing particles are much more likely to land there, and you grow these sort of ferny, almost fractal-like structures. Here's another picture. This one's a little bit harder to see, maybe. But this is a manganese deposit in a sort of block of sandstone, and again it's the same phenomenon. The manganese is diffusing in the sandy substrate before it's become solid, and you get the same kind of phenomena that we had before. These deep fjords forming and kind of ferny fractal type fingers. Now, lightning might not seem like a random growth process. If you think about lightning striking, this might not be an obvious example of random growth, but actually you can view lightning as a random growth process in the sense that when lightning strikes, the charges sort of explore the environment and they pick routes which have the least resistance, and those charges follow along those routes. And in that way, you can think about the charges sort of spreading outwards as corresponding to a random growth model. And you get sort of pictures like this, which in a sense can be almost sort of between the mineral aggregation and the biological growth. It's sort of round, but it's also got these sort of fingers start to form a little bit. And again, here's another picture. In this picture, this sort of, I guess, unlucky or lucky, depending on how you view it, this man has been struck by lightning. The lightning struck him in the shoulder here, and then it sort of exited down his back. And as it struck, again, the charges sort of spread across his back, creating this sort of electrical tattoo. And again, you can see, it was a different lightning strike. It's still random, but again, pretty similar sort of features to what we saw with the lightning strike on the pavement.
It stays for about a month, a bit less than a month. There are many documented cases when people survived and had these sort of tattoos on them.
Yeah, so don't go and stand in lightning just to get this, because it won't last. But it is kind of cool. I agree. Okay, and one final picture. This one's a little bit different to the other ones I've shown you. So this is something called Helly-Shaw flow. And what's going on in this experiment is we've got two plates of glass or perspex, and they're pressed very tightly to each other, so they're sort of very pressurized. And into the middle, between the two plates, we're injecting a viscous solution, like an oil or something like that. And what you might expect is if you're sort of squeezing oil into a space between two plates, you might expect the oil drop will just spread out uniformly like a circular drop. But as you can see, that actually doesn't happen. We actually see very, very similar phenomena to what we saw with the mineral aggregation. You get these fjords and fingers forming. And physicists believe that this model is closely connected to these models of deposition, but no one really knows why. And so this is a little bit different because we're not growing by successive particles being attached. We're growing in a more sort of smooth, continuous way. But I wanted to show you this one anyway, just because of the connection with the mineral aggregation.
So maybe if I say that it's really a wide open thing, which is actually of practical importance in oil extraction. But in an ideal world, ideal mathematical world, if you pump it, it will be ideal around, because just by symmetry, it will keep ideal around. What happens in real world, that glass is not absolutely flat, so in some place it's uneven, so unevenness starts, and then you destroy this. There are always random fluctuations in real world. So they destroy, and then once you get a random shape in the beginning, already even if you have everything regular, you will get shape like that.
Okay, so so we've seen that random growth occurs a lot in nature, and it's clear that we want to be able to study this. So in order to be able to study it, we need some sort of mathematical models. And in particular, the kind of questions we want to answer with these mathematical models is what happens to the randomness. So as we saw, at a microscopic level, at the level of individual particles, these processes are completely random. If I take two biological growths, there is no way that these particles are landing in any way in similar places. So at the level of individual particles, they're completely different. But yet when you look at large clusters, they somehow seem to exhibit this sort of predictable or universal behavior. And this is really what we want to try and understand by doing mathematics, is what happens to this randomness over large scales to somehow give us these similar kinds of behaviors. But also, why don't we get them in all the models? Why is the mineral aggregation so different to the biological growth? And so if we have mathematical models, we can perform simulations and do computations that help us try and understand the nature of this universal behavior. And in particular, what we're really interested in is when the particles are very, very small, because that's sort of realistic if we think about molecules or cells. But we also need the number of particles to become very, very large. So we want to study large clusters consisting of very, very small particles. And the mathematical term for this is a scaling limit of this model. It's a description of the limiting behavior of the cluster in the limit as the particle size goes to 0 and the number of particles gets very, very large. And so by analyzing these scaling limits of these mathematical models, we aim to sort of extract the principal mechanisms underlying this universal behavior. And so that's really the sort of aim of studying random growth is to answer these questions. Okay, so what kind of mathematical models can we build? Well, the simplest idea is let's just discretize our universe. So let's just imagine that we live on a grid, and that individual particles correspond to sort of vertices of this grid. Okay, so we start off with just one particle at the origin, and let's suppose we want to model biological growth. So what I'm going to describe here is a model called the Eden model. So what can happen? Well, this particle needs to reproduce, and it's got 4 available neighbors that it can, or directions that it can reproduce into. And each of these is equally likely, so let's just pick one. And now we've got a cluster consisting of 2 particles. Again, these particles want to reproduce, so where can they reproduce? Well, now we've got 6 possible neighbors for reproduction. And again, just pick one of them at random. We get that one. Again, now we've got 8 sites for reproduction. Pick one at random, continue in this way, and we get a cluster growing like this. As I said before, we're interested in scaling limits, so we want to imagine that our particles are very, very small. So we need to sort of zoom out, sort of shrink down the size of our lattice, and here we have our much finer lattice. But our clusters now become really, really small. So if we just kept the same number of particles in the limit as this grid goes to 0, we just don't see anything. So we also need to increase the number of particles, and if you do that, you start to get these kind of shapes. So this is a simulation of this Eden model with 1,500 particles, and as you can see, it's not a bad representation of reality. This isn't bad as a representation of these lichens or these mold clusters that I showed you. It's got the same kind of features. It's roughly round, but it's got these sort of fluctuations along the edge. So we have a mathematical model, and then the idea is to try and study the properties of this model. What about mineral aggregation? Well, again, we start with the same starting point. We started with this grid and our point at the origin, but this time we need a new rule for attachment. So instead of just picking each point in the neighborhood equally at random, we need to think about particles diffusing in from outside. So the way you can think about this is starting very, very far away, picking a random site very, very far away, and allowing a sort of simple random walk to take place on this lattice until it hits one of the neighbors. And when it hits one of the neighbors, at that point it sticks. So right now we've got 4 possible neighbors. We set up our simple random walk, and by the symmetry of the situation, each of these is equally likely. So just pick one of them. Now we need to do it again. We again start very far away, pick a random starting point, and perform our sort of simple random walk until it sort of hits one of these neighbors. But now things are much more difficult than they were in the biological case, because a random walk coming from outside doesn't see these 6 available slots in the same way. I mean, just locally you can see this one's got 3 possible places where the random walk could come in from. This one's only got 2 places where the random walk could come in from. So there's no reason why the probability of hitting this point should be in any way the same as hitting these 2 points, and in fact they're not. So these 2 points end up having a much higher chance of being hit than these 4 points, and that's what starts to grow this sort of fingery type behavior that we saw. Now, one of the difficulties now is you can start to see, even with only 2 particles, actually computing the probability of hitting these 2 points versus those 2, there's a computation that you have to do. And as this cluster gets bigger and bigger and more complicated, the computation gets more difficult and more complicated. So already you can see this diffusion limited aggregation model is going to be much, much more difficult to study than the Eden model. And in fact, I think in the 40 years since this model's been around, there's only been one rigorous result proved about this model. So this is really an extremely hard problem. But we have a model, so we can do simulations, and we can do the same things as before, shrink the grid down, let the number of particles become large, and you get this kind of picture. And again, it's not too bad at this level. It's got the fjords are forming, the fingers are forming. It's looking like a reasonable description. And in particular, it doesn't look like it's growing into a ball in the way that the biological growth did, the Eden model did. But actually, one of the sort of most interesting open problems is nobody can prove that this does not converge to a disk. So that's a really huge problem to sort of think about. It doesn't look like a disk. If you had to put money down and say, well, if I put a lot more particles in, is it going to turn into a disk? But nobody can say anything mathematically about this. So this is really one of the intriguing problems of the whole area of random growth is this eventually a disk? And if not, why not? Okay, and there's also some other lattice models for random growth. So I'm just going to briefly just describe the models. I'll do that on the board just to sort of just give you a flavor of the type of models which are out there. So again, as before, we have our grid, and we have our sort of seed particle at the origin, and we're going to attach particles one by one. And the rule is different for each of these models. So let's just suppose we've acquired a few particles. Okay, so suppose the cluster looks a little bit like that. So the first model is dielectric breakdown. Well, it's a whole family of models called dielectric breakdown models. And these are meant to represent the sort of lightning strikes. And so what you do with dielectric breakdown is we look at all of the possible neighbors that we could land on. And we work out the hitting probabilities of a simple random walk on these points. So the same thing that we had to do for the diffusion limited aggregation model. But instead of attaching according to the probabilities of each of these points, we then take these values, we raise it to some power, and we pick proportional to these values raised to that power. And the power that you choose depends on this sort of electric charge in the system. And so different powers give you different values. So imagine if we raise the power of 0, well, that's just giving the value 1 everywhere. And so we're equally likely to pick any of these neighbors. So we're back in the Eden model. If we take the power to be the value 1, then, well, we're exactly in the DLA model. And if we take values between 0 and 1, we start to get a range of different models turning up. And what's interesting about this model is, again, if you do simulations, you seem to be transitioning from round clusters, which are the biological ones, into these long fingery clusters as you change that parameter of the power that you're raising things to. Okay, so that's one another lattice model. The next one is internal diffusion limited aggregation, or IDLA. And what happens with this one is, in order to work out where to attach next, you also perform a random walk, but you actually start your random walk at the origin rather than from very far away. So that's what's called internal DLA. So external DLA, you start your random walk very far away. Internal DLA, you start your random walk actually at the origin. And what it does is it randomly walks until it first exits the cluster. And then the point it first exits the cluster, that's the bit that you add in. And this one turns out to be a lot easier to analyze than DLA. So quite a lot is known about this one. Then let's do another one. So the next one is something called first passage percolation. So again, we have the same situation as before. We start with a point at the origin, but we attach weights to every edge. So say 0.2, 0.1, 0.7, 0.5. Let's go 0.1. Just sort of put a few edges on. And what you do then is you grow your cluster by asking, how far can I travel in a certain amount of time? And the cost of travel, or the time it takes to travel, is given by this weight. So you let time increase slowly. This is a continuous time model. And so initially, the only place you can travel is just stay at the origin up until you get to time 0.1. And then you can afford to go along this path. So we add this point into the cluster. So we've now got 2 points into our cluster. Then we let time continue. So between time 0.1 and 0.2, the cluster just has these 2 points. At time 0.2, we can also afford to go along here. So this one gets added into the cluster. Then at time 0.3, this point gets added into the cluster. And you sort of carry on. Actually, we can add in this point as well. And you sort of carry on in this way. And again, you can see this cluster sort of grows by attaching successive particles one by one. And this model turns out to be quite closely related to this Eden model. So in the Eden model, we were picking each vertex uniformly at random. Here, if you choose your measure appropriately, you're sort of picking each edge uniformly at random, and you get similar looking clusters for that one. Okay, and I just want to give one final mention of something called interface model. So again, these are a little bit different. So these are growth models that happen in the half plane. So instead of starting with a point at the origin, we start with the half plane, and any of these points are good for growth. So let's just draw in our lattice. Okay, so the first model you can think of is a sort of deposition model. So what happens there is you've got big stacks of blocks living up here, lots and lots of stacks of blocks. And at certain points in time, an alarm clock rings and the block drops down, and you get a block down there. And then this alarm clock might ring and that block arrives. This alarm clock might ring again and that block arrives, etc. And so you sort of grow this interface in this way, and you can ask yourself about properties of it. So it's kind of like a boring game of Tetris, I guess. You know, you just got to watch it, and everything just lands on top of the previous thing. Now, this model is not very interesting because each column just evolves independently. But how it can become interesting is if you coat your blocks in glue. So this time, when a block drops down, it doesn't drop all the way to the bottom. It drops until it gets next to the highest block in the previous column. So if this column drops, the sticky side means it sticks to here, and so you get a block. You get a block over there. Then another one could drop through here. You've got another block there. Then if this one drops, it sticks to there, and so that carries on. This one here can drop all the way down. It's not going to stick to anything, and this model turns out to be very interesting because it has these interactions between neighboring towers. And again, it's conjectured that this sort of interface that we grow here has similar properties to the Eden model for biological growth that I described. And just one final discrete model I'll just tell you about is called the corner growth model. So you start off with a corner, and again we drop blocks down from the sky, but this time they're at sort of 45-degree angles, so little rhombuses, and they drop down until they hit the corner, and then they slide. And they slide until they stop sliding, and then they stick. So the very first one, no matter where it lands, is going to slide into the corner. Then the second one, when it drops, if it falls on this side, will sort of slide down to here. If it fell on that side, it would slide down to here. And we sort of carry on in this way, growing this cluster where these blocks just drop and slide. And again, you can see we get some kind of interface forming. And you can prove a scaling limit about this interface. It tends to look a little bit like that. But the really interesting thing is the fluctuations about this interface have exactly the same property as the fluctuations of this interface you have here. So these two models look kind of different, but actually they have very, very universal behavior again. And depending on how much time we have in the course, this is something we might get a chance to discuss at the end. Okay, so that's lattice models for random growth. Sorry, it's not. There's one. So the nice thing about lattice models, they're very easy to explain what's going on. You can draw a picture, you can visualize it. They're kind of nice, simple, discrete models to describe, but they're extremely hard to analyze. And there's very, very few rigorous results about them. And one of the reasons that they're so hard to analyze is we haven't really got any tools. You know, if you just look at this, I mean, how can I study this? You know, to have to describe every single height, I mean, that's a lot of information to keep control of. There's long-range interactions. There's really not a lot of obvious tools that you can use. And so the results that exist, the tools tend to be quite specialized to that particular problem, and they don't generalize very easily between different discrete models. But if we're working in 2 dimensions, we have an alternative to working on a lattice, which is that we can actually work in the complex plane. And the advantage of working in the complex plane, so we're viewing our cluster as a subset of the complex plane, means we can use complex analysis to answer questions about the geometric shapes of these clusters. And so that immediately gives us a tool. It doesn't necessarily make the problems sort of immediately tractable, but we've got some mathematical machinery behind the analysis that we can start to understand. So questions about geometry, about the shapes of these clusters, turn into questions about complex analysis. And so I'm just going to quickly finish by just describing a class of models called the Hastings-Levitov models. And these show how you can use complex analysis to describe random growth. And they give you sort of continuum versions of the lattice models that I've been talking about. Sorry, I don't know why I can't suddenly change slides. Okay, so here's the situation. You're starting off with just your sort of seed at the origin. So think about your electrode in your copper sulfate solution, and you want to attach a particle onto your electrode. Well, it turns out we're using the Riemann mapping theorem, which you may or may not have seen. I guess we'll find out when we see your questionnaires. But using the Riemann mapping theorem, we know that there exists a conformal mapping from the exterior of this disk to the exterior of this disk minus this particle. And you can see it's a conformal mapping. All of these rays intersected at right angles, and in this image map, they're still intersecting at right angles, despite this distortion that we've got over there. So we have a conformal mapping from this picture to this picture, and this conformal mapping, in some sense, represents the single particle. So instead of studying a particle, we can study a conformal mapping. And we can do it for whole clusters as well. So here's a cluster with several particles, and what I've drawn here is the mapping, again, from the exterior disk to the exterior of this cluster. And again, you can see, this is pretty distorted, but it's still a conformal mapping. These rays are still meeting at, are still preserving angles. And so if we can come up with an algorithm for constructing this map that corresponds to a cluster with lots of particles, then that means I can study the maps rather than the geometric shapes. And the maps are conformal maps. The maps are objects that I can express in the language of complex analysis. And so answering these kind of questions become questions in analysis. And again, we've got a lot of tools available to us. And so there's a good chance that this might yield some progress. Okay, so I've written up there the algorithm, but actually it's better understood if I just draw a picture. Okay, so the way we construct a cluster is we do it recursively. So suppose we've already managed to construct a map corresponding to a cluster with n-1 particles. So here's our big cluster with n-1 particles. And supposing we have a map phi n-1 that takes the exterior unit disk to the exterior of this map, and it's a nice conformal mapping with the sort of properties that we want. So for my recursive process, I now want to construct my map to a cluster having n particles. Well, how do I do that? Well, I know how to construct a map from the exterior of the unit disk to the exterior of the unit disk without one particle. So let's put our particle there. So the picture I showed you had the particle positioned at 1. I can just rotate that map, and that puts the particle anywhere that I want. So I've got this mapping Fn that maps to this particle, and the only thing I need to know what angle I'm going to put it in. So I'm going to put it in at theta n. That's how much I'm going to rotate the map, and also I need to know how big my map is. And suppose I want it to have length dn. So these are the two inputs that I've got. So given this angle and the size, I can construct this single particle map. Well, what happens if I compose these two maps together? Well, this particle is in the exterior of the unit disk, and the exterior of the unit disk is mapped by this map to the exterior of this shape. But they share a common boundary, and so the particle's got to share a common boundary with this. And so that over there is my phi n-1 of Pn, if this is the particle Pn. Okay, but what have I actually got on the right-hand side? I had n-1 particles making this up, but now I've got something else stuck on. So that's n particles. So the exterior of this is actually the exterior of a cluster with n particles. And so that means that my composition map does exactly what I want. So I can set phi n to be equal to phi n-1 composed with Fn. So there's my recursive process, or you can sort of extend this to go F1 up to Fn. So what did I need in order to carry out this process? I needed to know what angle I was putting my particle at and how big I wanted my particle to be. Those were the two inputs that I needed. And if you gave me any sequence of angles and any sequence of sizes, I could apply this process and give you a sequence of conformal mappings corresponding to those shapes. And so choosing these parameters actually allows us to describe a wide class of growth models. And in particular, we can grow all of the ones that we saw before, the Eden model, DLA, dielectric breakdown, by choosing these appropriately. And this is this Hastings-Levitov family of models, and this is what we'll talk about in the course, is actually how we choose these parameters in order to do that. But I'll just leave with some simulations just to show you the sort of pictures that we get. So here's our biological growth. So again, you can see it's got the right kind of behavior. These colors correspond to different epochs in time. So the black ones arrived first, the pale blues arrived last. And you can see it's growing like a disc, but with some sort of roughness at the edges, as expected. Here's a sort of our intermediate one. So this is one of these lightning strike models. And again, we start to get some sort of irregularities going on. But internally, you can see the sort of Fermi type behavior that we're used to. And again, here, this is the one corresponding to diffusion limited aggregation, or the mineral deposition. So again, we're getting these deep fjords, we're getting the long arms, and it's got the same, but internally we've got these sort of fractal Fermi looking behavior over here. Okay, so just to sort of summarize with what we kind of intend to cover in this course. So a lot of these models, we do need to know a lot of probability theory and a lot of complex analysis in order to even describe the models. So half the course is going to be complex analysis and probability. Depending on what we saw in your questionnaires, we'll adjust that accordingly. But this will allow us to have the knowledge of the results and the language that we need in order to construct these models. Once we've constructed them, we can then ask the sort of questions I've talked about. What are the scaling limits? Are there phase transitions from sort of round models to not round models? What other properties do these models tend to have? And as I sort of already suggested, these questions are very, very difficult. And so a lot of what we're going to talk about is actually conjectures and open problems. There's far more questions than solved problems, but it's important to see this and see how rich it is, and again see how you can start to make progress on some of these problems. Okay.
Yeah. Okay. So I want to say a few more pictures. So it's to show a few more pictures. So the interesting thing about those models Amanda was speaking about, it's actually not quite true that all of them. Yeah.
Sorry.
So I'm going to show a few more pictures, and I must say that not all of the models here mentioned here, they have something to do with complex analysis. And sometimes it's mysterious why some of them have and why some of them have not. So there are here actually two simplifications besides the complex analysis. Just plane is easier than three-dimensional space. So if you draw a coral in a coral-like shape in 2 dimensions, just there are these fingers, one-dimensional fingers. If you do it in 3D, it might have more complicated, intricate structure. And the second is that indeed there is complex analysis. There are some similarities to complex analysis in 3-dimensional space. So here much will be around the Laplace equation. So Laplace of h is derivative in x plus derivative in y. And it's kind of, the most fundamental differential operator you can write. It's rotationally invariant and the only one like that of degree 2, and many physical processes, well, I don't know, 2/3 of physical processes are built on this operator, like heat conduction, for example. you can also study in dimension 3 this operator, but it's much more difficult. So there are several reasons why it's much more difficult. Harmonic functions, they exist in dimension 3, but for example, in dimension 2, there are analytic functions which are nicer. Now, the problem with all these models is that they're incredibly difficult. So there are more open questions than there are closed questions. And Amanda said about the scaling limit. For example, this Hastings-Levitov, there is no, for most interesting values of parameters, there is no clear scaling limit. Now, there is one miraculous case where there is. So, for example, we don't know, well, if you do this thing, we don't know, or at least I don't know, a satisfactory, interesting scaling limit when you can attach these disks wherever you want. So, for example, DLA, this coral-like shape crystal deposition, it's an open question whether there is a scaling limit or not. People don't know, physicists don't know even. Because there you have to have idea without a proof, and even without a proof, we don't have idea whether there is it or not. Surprisingly, there is one case if you attach all the blue disks at one point, so we keep attaching them at the, you attach n plus first disks at the previous one, there is a very nice scaling limit. And it's also related to these models in a different sort of way, where you try to construct this dynamical fronts in a sort of a static way. So I'll switch to another set of slides, because I need to show a movie, so I need not PDF but PowerPoint. So what you see on the right is a picture of an erosion. So in this particular case, there is aluminum film. So it was done by people at the Koebe Polytechnic, aluminum film on glass, and there is a drop of acid and it's eroded. And to the left, there is a movie demonstration of how erosion works. So in a sense, it's just the inverse of deposition. You chip off particles one by one. And again, well, there are different rules you can come up with. You can come up with a rule that just you take a random particle on the boundary uniformly and you chip it off, or you can have a rule that there is a wind or water, so the more exposed the particles are, the more likely they are to be chipped off. What happens is it's sort of interesting, because physicists have been studying these models from 50s and 60s, and I was just Googling yesterday for a picture, and I miraculously find a picture from a popular book in Russian, which I read when I was a school kid 30-something years ago. So it calls Physics and Geometry of Disorder. So if you, well, Russian letters are like Greek, so you can actually guess that this is physics. It starts with phi. There was a picture of experiment taken with electron microscope. So this is a deposition. So this is a crystallization of gold. So you get larger crystals, and you see you get some fractal shapes. Here there is a sort of picture which is sort of forest fire, where you have again this cluster of burned out trees. For that, those are dynamical processes, but for that a static model was proposed by two British mathematicians, Broadbent and Hammersley, which is called Percolation, and it's a very easy model. So you can think that it's a model of epidemic spread or forest fire spread or traffic jams in the city. So you have a perfectly rectangular city. You can think of Manhattan. And every road is open or closed independently of each other with probability p open with probability 1 minus p closed. So this is high value of p, almost all are open. This is low value p, almost all are closed. So it's clear when p is small that you can't move very far. Eventually we run into closed roads. So if it's summer and everyone is on vacation, they start renovating all the pavements in Manhattan, then there is a good chance that you run very fast into something very close. On the other hand, if almost everything is open, you can move around freely. So the interesting thing which happens in this model is that if you change p, the properties, of course, for a finite size Manhattan, for a Manhattan like 20 by 20, anything you can write will be a polynomial in p of degree at most 400. So for example, probability that you can reach north side from south side, you can drive all the way from downtown to uptown, will be polynomial in p of degree 400. if it's million by million, it will be polynomial of p of degree. Million by million area is what? Trillion. Polynomial of degree trillion. But polynomial theory of degree 400 can approximate very non-smooth functions fairly well. So what happens here that there is basically a jump-like behavior, that there is some critical value of p. In this model, it's a theorem, a famous theorem by Kessler, that it's 0.5, that up to this value you can almost with big probability pass from downtown to uptown, and above this value you cannot. So it's not that you continuously move from this to this, but there is a regime where the whole forest burns, you can drive throughout the whole city, and there is a regime where you immediately stop and where nothing burns. You can actually see it with epidemics, that if parameters change, you don't have an epidemic, there are a few people who are having influenza, and then suddenly either temperature changes or the virus becomes different, and immediately everyone is ill. So there is phase transition with ubiquitous. Now you can do it on any graph. You can do it, for example, on a square lattice, but with sides, not with vertices. Then the PC will be different, 0.59 approximately. It's not a number which has some meaning, but the properties will be the same of this phase transition. Again, you cannot go on white here very far, here on black here very far, here you can go everywhere, and this jumps at this port. And the interesting thing is that there are these three regimes. Everything burns, nothing burns, and there is a fractal regime where something stops on PC. And the fractal regime is important, and you see it in real life, because if you have like a forest which is burning, it can stop at a straight line when it reaches a railroad or seashore or something. But if it just stops in the middle of the forest, what will happen? If P is large, everything will burn. If P is small, it doesn't burn at all. So the region where it stops, if you have fluctuating P, is approximately region where critical P is. So we will see this critical phenomenon in real life. And this is also the reason why this statical model can be used to approximate some of the deposition growth models we have seen before. Not all, but some of them are related to this one. So here, for example, what happens if you start a fire in the middle of a forest and you change P? For small values of P, only small region will burn. For large values, everything will burn. And for critical P, there is this sort of fractal shape, which is reminiscent of something we have seen before. So the spectacular thing which happened with this model, that people, experimental physicists, they were observing it in the lab. They were like burning forest and counting the length of the burned curve. Well, you don't need to burn forest. You can take aerial pictures of some California forest fires. And they proposed, said, this percolation picture, and they were numerically studying what are the different exponents. And for example, like Bernard Sapoval, who's a famous physicist at École Polytechnique, he did many practical things as well. He conjectures that the boundary of burned area is fractal of dimension 4/3. And at the time it looked a bit science fiction, but then other physicists came and said that with the use of complex analysis you can actually explain how this 4/3 comes to be. And the example of explanation, so this is what follows from some part of field theory. So field theory studies, well, quantum fields, and part which is called conformal field theory, it studies specific case of fields which you can think of as random functions or random distributions, if you wish, on a plane, which have something to do with complex analysis. It turns out that in this particular case you can calculate many things, and if you were to relate them to lattice models, and lattice model kind of gives you a discrete field, discrete random object, then for example for this one you would get these three predictions, that the leftmost crossing or the boundary of burned area is a fractal of dimension 4/3. It means that if you have 1000 by 1000 box of trees, it will have approximately 1000 to power 4/3, 10,000 trees, so it will be very, very windy. But what is more interesting, that the whole burned area, blue in this picture, will have dimension 91/48. So 4/3 sometimes you get in mathematics from some simple argument, 91/48, it has to be a bit more complicated. And then there are more interesting that, for example, probability that if you start fire at 0, that it spreads everywhere, so 0 connected to infinity, behaves for P bigger than PC like P minus PC to the power 5/36. So there are many predictions which seem to, when they appear, they start appearing in 70s, and then they actually started, the predictions from this theory start appearing before, 10 years before this theory was there. Just people didn't know they were using it. And then mathematicians started trying to understand it rigorously, because here, for example, it's a perfectly rigorous statement in our form field theory that something is equal to 4/3. But relate this something to percolation is very difficult. And mathematicians were able to do it, and well, one of the first steps was done by that Schramm, who unfortunately died in a hiking accident 10 years ago. So what he suggested to do not a growth problem. He suggested to take this, for example, percolation picture and explore the frontier between two clusters, white and gray. So we can do it dynamically. You can draw this picture dynamically, but in fact, it's, as far as two dimensions are concerned, it's static. I've given you a percolation picture, and then there is a person who walks using left-hand rule. So it's actually very easy in the sense that this person, it can be myopic, it can see just one step away, and still he's able to follow this thing. So this gives me, you have a random picture. For every random picture, I have a broken line. So I have a random broken line. So Schramm proved lemma, which was sort of incredibly shocking at that time, that if you have a curve which has something to do with complex analysis, then this random broken line has a scaling limit. And it's has only one parameter involved. The parameter depends on which model you started with. And so he called it stochastic Loewner evolution. Now it's called Schramm-Loewner evolution. And this is a thing which describes how this curve grows. So one way to grow this curve is that it's very similar to what Amanda said, this composition of maps. So you can just split these curves into a few steps and then just compose maps which open up the slits. There it was half disks, here it's just a slit, or you can draw it continuously, just draw till time t, and gt is the map which opens it. So it turns out, it was known for over 100 years by Loewner, that this map GT satisfies very, very nice, easy equation, which has only one parameter, WT. You can view it as how you steer the steering wheel when you drive along this trajectory. So there is a Euclidean version. If you drive car at 60 kilometers per hour and you steer the steering wheel, if you know how you steer the steering wheel, you can reconstruct the trajectory of a car. Only you need to solve an equation. Now, if you drive a car, you can reconstruct the steering wheel, you just drive the car along this road and you see how it steers. So here is the same, only it's in hyperbolic geometry. So it's hyperbolic speed of 2 hyperbolic miles per hour. Not, well, for some historical reasons, there is a number 2 here. You can put number 1 to be more logical. And it turns out that if you plug in steering function, which is Brownian motion times kappa, then you get fractal curves because you jerk it fractally, and they're different for different values for kappa. Why? Different because you drive with the same speed too, but you jerk your wheel with different speed. So the more you jerk, the more fractal it will be. And since Schramm proved this like 10 years ago, there were a number of models. Oh, that's actually, yeah, that's a very interesting story. Well, I'll say maybe more words later, but Loewner proved and first made a sort of first or second step in proving Bieberbach's conjecture, and I'll say more a little bit about it later. So that's the title of the paper, and number 1 was aided by Bieberbach, who was editor of the journal, because he was so excited by this paper by a young graduate student. He thought that certainly he will solve my conjecture soon, and there will be number 2 part. And number 2 part never came. It was done by another guy some 60 years later. So it's, yeah, so those are examples, the case where it was proved. So this percolation, if you take this curve which goes around the cluster, it is a fractal curve of dimension 7/4 and corresponds to parameter 6. If you don't go into fjord, so you take only the outer boundary of this curve, so this will be this sort of diffusion curve or forest fire curve, it's parameter 8/3 and dimension 4/3. You can do another simple model. So this simple model is called uniform spanning tree. You take all the possible labyrinths with equal probability. You take all the possible trees, all the possible labyrinths you can make out of a square. So the limit will be a random piano curve of dimension 2, and it's apparently is described by this sort of Loewner process parameter 8. If you take one branch of a tree, it will be parameter 2. Now, those of you who did some statistical physics course must have heard of Ising model. So that's perhaps the sort of most ubiquitous model in statistical physics, model of ferromagnet. It's not like percolation where you toss a coin. You ask nearby squares to try to be of the same color with certain weight. So this model, what it turns out, so there is a picture what happens if you change the temperature, and there is a frozen phase which Ivan Velenik, who is also at our department, completely described. They described it in this case. What you get if you enforce two phases, then the boundary between them there will be like straight line with a small random walk fluctuations. Now there is a critical regime and there is a high temperature regime. So high temperature regime should be the same as percolation, but we don't know it yet. So that's a big open problem. But for critical regime, we could prove that there are fractal curves, and those are related to SLE3, SLE16/3, so different fractal things. Now, one more thing. So these are all models where you do different coloring of the plane, and then you look at some interfaces. There is a model which was introduced by Paul Flory, Nobel Prize in Chemistry, as a model for position of a polymer molecule in space. So polymer molecule can be very, very long. Like if you put together all the pieces of your DNA and you straighten them up, that will be 2 meters. Now, of course, DNA inside our body, it's sort of squeezed in a tight ball. But there are situations where DNA unwinds, there are situations where polymer molecules unwind. So those are actual pictures under tunnel microscope of some molecules. So what he proposed is you take a random walk on a plane, or in 3-dimensional space, you condition it to be simple. So it's no longer a good process because you can draw a curve where the tip is exposed and it's easy to go far. But you can also draw a curve where you're not around, and then you are in a dead end, you cannot leave. So it's difficult to define it as a process. You can define it just as you take all the curves of length n, you throw away those which self-intersect, and you take one at random. So it is supposed to be SLE 8/3. So this is this curve. It's very like the actual pictures of polymer molecules in dilute solutions. And it's supposed to be the same as a boundary of percolation clusters. This is the boundary of percolation cluster, so they're supposed to be the same curves. So here we prove that it's SLE 8/3, and it's supposed to be the boundary of Brownian motion, also SLE 8/3. So in these two cases we know it's a Brownian motion, it's a percolation, and that should be the same curve. And so this is SLE, the Schramm's idea. It's kind of a successful example of conformal growth where, in a sense, we reach the ultimate goal. We have a very neat object about which we can say everything. In many cases, we prove that it relates to something. And it would be very nice if there would be such object when we grow not at one point but everywhere. Now, I want to show 2 pictures of what is sort of related. So this is very much like that picture, but not in dimension 2, in dimension 3. So you have a corner of the room and you drop small cubes there. So this particular one actually there is a room 40 by 40 by 40, and you take some position of cubes in the corner at random. So you see that what happens here, it's quite interesting that it turns out that there are these corners where it's very ordered, and it has nothing to do with complex analysis. But this part is supposedly has to do something with complex analysis and very much related to percolation problems and such. And this is an example of an open problem where it's half done. So there are lots of very nice work by Kenin, Akunikov, Borodin, and many others, but it's sort of semi-open. But on the other hand, there are regimes for this model. There are regimes where it's frozen. Now, I think we ran a bit over time. I wanted to show maybe that there is some limit. So to show a couple of slides from 2 of my friends who do related things. So this is, let me see what did I want to do. So this is Jeremy Quastel, who is a professor in Toronto. So this is something which Amanda mentioned. Yeah, okay. Yeah, that's very funny. It's called KPZ fixed point. So there are 2 KPZs in this science. One is, I said, Belявin, Polyakov, Zamolodchikov. There is also a paper, Knizhnik, Polyakov, Zamolodchikov, which is abbreviated to KPZ. And there is another paper, Kardar, Parisi, Zhank, which is also abbreviated to KPZ. And both of them have dimension for thirds for similar objects, but for very different reasons. So this is Kardar, Parisi, Zhank, and this is a case where they can sort of write equation for deposition, and this is one of the pictures Amanda had, well, this is so what did I want to show? I wanted to show these two things. So there are processes, it's very interesting. So if you do burning paper, it's very different from burning forest. So burning forest essentially burns in no direction, but burning paper, the air, the carbon dioxide, monoxide has to escape. So there is always a direction which is preferred for burning. And then it's different. And also coffee stains are very different from tea stains. So one of them is one, I think one of them is one KPZ, another is another. So it's kind of interesting that they have the same dimension allegedly, but they for different reasons. And also, well, that's kind of a thing that this deposition of squares, it's related to some process of particles moving on a line. So so that's just sort of one example that there is a big activity in the same area about the same problems, but it's not related to the complex analysis we are going to be discussing, and it gives very interesting things, but slightly different. So it's kind of saying that there are many areas which relate to this. Now we take now a break, and then we start with some background in complex analysis. Now we went over time, so let's do a 7-minute break. Yeah, let's do, well, 5-minute break. Yeah, that's 5 minutes. 7 is too much. Yeah, that's not much. So I want to do in the next 2 hours, next 4 hours, some sort of crash course on complex analysis. So now, everyone has seen analytic functions, so I'll just briefly remind. So the function is called analytic. So analytic function. By the way, so there are still two words which are used in different areas of mathematics, homomorphic, and this is the same as also regular. F is a function from omega to complex plane, so it's called analytic if for every z in omega there exists complex derivative of f. So it's a limit as, let's say, delta goes to 0, f of z plus delta minus f of z over delta. Now, sometimes we will have functions which go to complex sphere, and then we call them meromorphic. So it's maybe the easiest way. It's people either write formulas separately for the case where value at z is infinity, because, for example, then such thing doesn't make sense. But one way in this case is just there is a complex sphere, there is point at infinity, just rotate this sphere so that infinity is no longer infinity, and just work with this formula. The formula for rotation of the sphere everyone can write. Well, so the reason why there are so many different words is that they have many different properties. Maybe I'll just remind like 5 of those. So the following are equivalent, the first one is the property is that f belongs to holomorphic, which means that there exists derivative. Second property is that f, so that there is a primitive f capital, so that f capital prime is equal to f. So in every neighborhood, so for every z, there is a neighborhood such that f of z plus delta can be written as a power series expansion. or if that for every gamma, which is a contour with no holes, contour integral of f of z, the length of gamma is equal to 0. So this is just if you haven't seen it before, just a Riemann integral where you take the sums of fzj times dz, well, dzj minus dzj plus 1, so it's kind of, well, you just do the sum along such vectors of this thing, and then you send the length of the vectors to 0. So this is basically the very sort of powerful thing. I'm not going to prove it. I'm going just to point out that, for example, well, this is the redefinition. So this is a function which has this property is called holomorphic, function which has this property is called analytic, and the function which has this property is called regular. Originally, that was there, and then it turned out that the three properties are equivalent. This is perhaps the easiest property to check because it doesn't involve derivative or primitive. It just involves that you take integral and integral is equal to 0. So for example, what we'll have in this course, that we'll have a sequence of functions which are analytic. We want the limit to be analytic. If they converge, fj converges to f, then integral of fj converges to integral of f. Integral of fj was 0, integral of f 0, so we are done. Now, this property is related to the property of the primitive in the way that it just says that, so this property essentially can be, so this integral being 0 means that integrals like this and integral like that are the same. So it means that if you define primitive of our function integrating with respect to some path from x to z, it's independent of the path. So essentially this property is the same as that there is a primitive. Now, how to relate the other properties? Well, that's more complicated. It's related through the, well, again, let me just maybe say a few remarks and a few properties so that so the most important property is the Cauchy formula. So it says that f of z. So again, we have a contour, and f is analytic inside, or holomorphic inside of gamma. Then f of z is equal to, for z inside this contour integral of gamma, f of zeta over zeta minus z d zeta over 1 over 2 pi I. So this is basically the root of all the nice things about holomorphic functions. So this is actually, oh yeah, this one should be never put into the water. Yeah, so it's because it basically says that there is one holomorphic function, one important function, 1 over z. And all other holomorphic functions can be written as combinations, integral combinations of it. So there is a fundamental solution to the operator d bar, which we have not read, which I haven't written up yet. It's 1 over z, and because of that, so it's everything is nice. And it's very much behaves like potential theory in physics, and we'll see some potential theory a bit later today and in a week, with only difference that our potential is complex. So it's a vector potential. So for example, it can be cancelled out, so you cannot define things like capacity. For example, you can define capacity for this potential. And the usual capacity is, it's quite clear that it's subadditive, that if you take two conductors, then the joint capacity, you can put at least as much as in the sum of two. So here, for example, for this potential, it was a big open problem all the time when I was a student. It was proved just 10 years ago by Xavier Tolsa from Barcelona. So it's kind of, well, around this thing. And this allows to prove all these properties. For example, what is important here is that if you want to differentiate this thing in Z, what you get, let me just use another kind of chalk. If you differentiate in Z, then here what happens is just you differentiate in Z, you get this formula. So derivative of f can be written in terms of f as integral. So if you know f on the curve gamma, you know derivative inside. And you know derivative of derivative and derivative of derivative and so on and so on. And that gives you this formula with the power series. So this gives you Taylor form. So it's indeed the most sort of important formula, and it's very, very, very nice. Now, why we ask the function to have a derivative, and suddenly we get these nice properties. If you own an integral, you never get nice properties from function having a derivative. Because actually by asking it to have a derivative, we impose one condition on another derivative. So the usual the usual thing how you would write what you would write f of z plus delta is equal to f of z plus delta x derivative of f in x plus delta y derivative of f and y plus small order terms. So this is the usual like Taylor expansion, plus delta x delta y plus delta x squared delta y and so on, these order terms. So here I just mean that delta is equal to delta x plus I delta y, or delta z. Yeah, maybe just write delta z. Now we can rewrite it also in terms of delta z dz f and delta z bar dz bar f, where basically, so what I mean, so delta z is this, then delta z bar is just x minus iy, so it's these two things. So it's clear that there is a linear relation between delta z bar and delta x delta y. So if I have formula with them, I can rewrite it into this one and the other way around. And basically, what does it mean? That f is holomorphic if and only if dz bar f is equal to 0. So it's basically condition of being holomorphic, just condition then one of the two derivatives is 0, that there is no this term. And this is what is usually people write as Cauchy-Riemann equation, and Cauchy-Riemann equations I never can remember the signs there for obvious reasons, because the signs they are product where we have coordinate x horizontally, then coordinate y. If you exchange the labels, then the signs will change there. So it will be, so it's sort of artificial. It's the fact that we choose that we choose the counterclockwise direction to be this, if we choose the opposite one. But just for the future reference, so in case, so it's, so what do we have from this formula? From this formula we can also write the opposite one. So from this formula and that we get that dx is dz plus dz bar, dy is I dz minus I dz bar, and also then you can write that dz is dx minus I dy over 2, and dz bar is dx plus I dy over 2. So that's the formula. So the Cauchy-Riemann equation is just dz bar is equal to 0. So the Cauchy-Riemann equation, the way people usually write it is that well, dxf plus I dyf is equal to 0, but then you also write that f is u plus iv, and then you get equation from yeah. So if f is u plus iv, then these two equations they mean ux equal to vy and uy derivative is equal to minus vx. Okay, so that's the analytic functions. So what else? What do I need? Any more properties? Well, maybe just the third property is that there is a maximum principle. So analytic function achieves maximum on the boundary of a domain always. So maximum of f
on the boundary of omega is equal to maximum of f on the omega. Then there is the mean value property, which is actually more strong, which is actually much stronger than maximum principle, that f of z is equal to 1 over 2 pi, for example, 1 over 2 pi integral of f on a circle around z, f of z plus, let's say, r e to the power I theta, d theta. And the one which, yeah, and of course it's the space of, it's not compact, but it's complete. So the space of analytic functions in some domain is complete. So if there is a limit, then it's analytic just because you check this property, as I said. And the one important one, I think almost everyone has seen, is argument principle. So if you have a contour gamma, then the number of zeros of f inside gamma minus number of poles of f inside gamma. Now poles if f is meromorphic, if it can take value infinity. If it doesn't take value infinity, then there is this term. This is equal to the integral the length of gamma of log f prime dz. Okay, 1 0 1 over z 1 over 2 pi I. So this basically how does this work? So we map it by f. And we want to know how many zeros is there. So you look at this curve, and basically you need to count how many times it goes around 0. And that will be the number of zeros. So this is, in the terms of logarithm, what it means is that the logarithm function, its real part is single valued. But its imaginary part, when you go around 0, it increases by 2 pi I. So each time when you go around 0, it increases by 2 pi I, so you divide by 2 pi I, then you get number of zeros. If your function can have also poles, then each pole will contribute -1. It's like 0 upside down. Okay, you also should remark here, I should remark that you count them with multiplicity. So with multiplicity, so it's... And if you want not numbers of zeros, but numbers of f equal to a, then you get logarithm of f minus a. So it's okay. So that's probably everything we need so far for analytic functions. Now the other class of functions which is very important for us, it's harmonic, and h from omega to r, or c usually will have real valued, is harmonic if h is C2 and Laplacian of h is identically 0. Now Laplacian of h, it depends whether you talk to mathematician or physicist and the area of this person, what is Laplacian of h. So usually people say that it's hxx plus hyy. Second derivative in x, second derivative in y. Some people put some factor in front. Some people put minus in front. It's just a question of convenience. In different areas, it's slightly different how they do it. Now, why people would want to put some numbers in front? Well, there are a few properties. The first property is that dz times dz bar of h is equal exactly 1/4 of Laplacian of h. So this is just the thing, if you combine these two guys, what you get, dx, second derivative in x, minus I squared dy, minus I squared is plus 1, so we get second derivative in y. And dx dy, they will cancel out, because one will be with I, one with minus I. So some people, because of that, call Laplacian this thing divided by 4. But yeah, maybe also, yeah, for simplicity, you know, sometimes people denote this d bar. So some people just denote d bar. So probably eventually I will be lazy and denote d bar as well. Okay. Now, so that's the first property, trivial one. Now, the second property is that if omega is simply connected and H is harmonic, then there is H tilde harmonic such that H plus I H tilde is holomorphic in omega. In the other way around, so if F is holomorphic in omega, F is equal to H plus I H tilde, then H and H tilde are harmonic. Well, why the second part, why H and H tilde are harmonic? Because Laplacian is just d times d bar. If d bar is 0, then d times d bar is also 0. So that's it. So proof. So who has seen these properties before? Okay, who hasn't seen? I was fun, like people don't like to raise their hands. Yeah, so we should start with some physical exercises. So the proof, the second one is very easy because delta F is equal to 4 df d bar F. D bar F is 0, so it's 0, which means that delta H plus IH tilde is 0, which means that they split into real part and imaginary part, and that's it. So that's the second part of the proof. And the first part can be done in several ways. It's perhaps the first one, what you can do, well, if you haven't seen it, I can leave it as an exercise. So one can construct H tilde by some sort of integration trick. But look, we don't need to construct this function f and prove that it's analytic. It's enough to construct primitive of f or derivative of f. And derivative of f, because we know the Cauchy-Riemann equations, derivative of f can be written in terms of just its real part. So so what you do for the first one, we take function g, take function g of z to be well, we need to do something like hx of z plus ihy of z. And the exercise is to figure out whether it should be plus here or minus here. So it should be ux plus uy. So I should have what? Minus vx, yeah. I think it should be minus. So exercise is to figure out whether it's plus or minus. Prove that G is holomorphic. So the check Cauchy-Riemann equations. Then take f to be primitive of G. And f will be h plus ih tilde. So that's one possible proof. So if you haven't seen it, it's better to work out. We don't need the proof, but it's just to sort of be more comfortable with the analytic functions. Well, what else? What else? Well, okay, so H is harmonic. Then you have mean value print property. The same because it's real part of analytic functions, so it's mean value. And then there is, of course, maximum principle, because you have mean value, so maximum is attained on the boundary. So maximum over omega of H is equal to maximum on the boundary. And maybe, well, the fourth one is, again, that it's analytic. You can write a power series expansion, but not a complex one. You have powers of delta x, delta y. So I just tried that H is harmonic. It means that H is C infinity. So I think that this is what is important to understand about analytic and harmonic functions, that once you sort of fix this definition for analytic functions, it's not that you ask that it has a derivative, you ask that it has a derivative, but also another partial derivative is equal to 0. And that imposes a very, very tight condition, which, for example, means that if I have an analytic function in domain and I know its values on small interval, I know its values everywhere. And not every value on small interval will work out. So it's very, 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 very rigid. So it's not like having differentiability on a real line. Now we will use a lot in this course conformal maps. So okay, there is a dry one. So conformal map is just an analytic function which is a map. So conformal maps can be also, well, yeah, there are definitions in higher dimensions, but they are not that interesting there. So conformal map. Again, there are different words people use. Univalent map, and also the German word schlicht is used historically. So conformal map is a function, well, let's say f from omega to complex plane, which is 1-to-1 and holomorphic. So it's just a holomorphic map, 1-to-1 map. Again, there are several equivalent properties. So the following are equivalent. So the first f is conformal in the sense of definition above. And the second, this is the root of the word conformal, f preserves form. So f is a C1 map, and f preserves angles. So this is like a picture Samantha was drawing, that you take a map, you take, well, grid or, well, anything. And then what conformal map does, it does not map straight lines to straight lines. It maps them to some smooth curves. But for example, I had here 3 horizontal and 3 vertical, and it will map them to 6 lines which also intersect at 90 degrees. So it's a local property. So globally things are perturbed, but locally they are not perturbed. And it's easy to see because analytic function locally, it has a complex derivative. So local analytic function, it's a stretching and rotation. So locally, if you blow up this place, so if you blow up this place, then what you see is just this thing and this thing, they're almost the same. So there is second order perturbations, but otherwise they are the same. Sometimes people say that not preserve first angles, but preserves small circles. Or infinitesimal circles preserves infinitesimal circles. What that means that if I take a circle of small radius delta, then the image is circle of some radius up to delta square perturbations. So it's not an ellipsis, it's indeed a round thing. Okay. Now, two remarks about important properties. So if f is holomorphic and f of prime of z0 is non-zero, is the same as saying that f is conformal near zero, near z0. Why? Because f of z0 plus delta is f of z0, so let's say proof, plus delta f prime of z0 plus delta squared f prime prime of z0 plus small order terms. So if f prime of 0 is 0, then you start with the next term and it won't be conformal. Well, every value will be taken at least twice. But if you have this, whatever is remained is much smaller than this, so it will be to the first order linear, and you can easily, using implicit function theorem or argument principle, deduce that it takes every value exactly once. So until you reach delta where these terms will sum to something comparable, it will take every value exactly once. So this is much smaller. So why don't I just write the definition of conformal that derivative is non-zero? Because locally conformal derivative is non-zero, but what you can have a map of a disk on a domain which overlaps with itself. So for example, these two regions, they are mapped one to this side and another is mapped from that side. And then it's no longer conformal in this place. But locally derivative is non-zero. So conformal is this local condition plus a global condition that there are no overlaps. Okay. And the second important property is that, let's say, conformal maps preserve harmonic functions. Map, let's say, phi preserves holomorphic and harmonic functions. So if f is holomorphic, h is harmonic, then composition with phi, f of phi is holomorphic, and h of phi is harmonic. Well, the first is clear because composition of holomorphic functions is holomorphic, so it's more general because you can, each of them has complex derivative, you start differentiating, you get complex derivative. And for harmonic it's true because every harmonic function can be complemented to be holomorphic. Yeah, sort of, I have that written it on the blackboard, but it's sort of clear, I haven't written, but it's clear that if f, g are holomorphic, then f plus minus g, f times g, f of g, they are all holomorphic functions. Because whenever you have a formula for differentiating, whenever you have like chain rule or product derivative of a product, then you can write that there is a derivative, so we get that they are also holomorphic. Division is slightly difficult because you should be careful that you don't divide by 0, otherwise you get meromorphic function. So this belongs to holomorphic only if you don't divide by 0. Okay. Now there is one really important theorem which is called Riemann uniformization theorem. Yes? Yes.
It's a one-to-one and holomorphic. Is it automatically an open map?
Automatically what?
An open map.
Yes. Yeah.
So if so, it's going to be biholomorphic if the derivative is always non-zero.
Yes. Yeah. Yeah. It's well. No. Conformal map. Inverse of conformal map is a conformal map. Yes. Yes. Yeah. 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 So that yeah. I haven't said this, but and it will be in the exercise. There will be some problems about conformal maps, but for conform, so okay. Obviously, this is not true that sum of conformal maps is conformal map, because sum of one-to-one maps is not necessarily one-to-one. But what is true that composition of conformal maps is conformal, and the inverse map is also conformal. Yeah. So they kind of form what's the proper word? It's pseudo group. I think that you can compose them by composition, but of course you need that. So if map phi maps from first domain to the second and map psi from the second to the third, then you can compose them. At least as long as it makes sense, this definition. Yeah. And the reverse also is conformal. So the most important theorem in complex analysis, the Riemann uniformization theorem, which says that for any simply connected omega, there is a map phi to either a complex sphere or complex plane or unit disk. So D is unit disk. So more generally, it's true if I take any simply connected manifold, if I have any simply connected manifold, two-dimensional manifold to the what's called Riemann surface with complex structure, then it can be mapped to one of these three. So in particular, in this case, let me just say, so if omega is inside complex plane, then you cannot have this case of complex sphere. Is to, if omega is inside complex plane and not equal to complex plane, then omega is mapped to the disk. So basically you can have the full sphere, you can have the full plane, or everything else is mapped into the disk. Now this is actually a sort of much bigger theorem in a sense than just complex analysis. It's a classification of two-dimensional geometries. It says that if you have a two-dimensional geometry, then you can map it by map which preserves angles, so preserves geometry. You change metric, meanwhile, by some factor in different places, different factor, and you can map it to one of three geometries. This is a round bow geometry. It's a geometry of positive curvature where the length, where angle at every point is more than 360 degrees. The length of the circle is less than 2 pi on a surface of a bow. Or flat geometry where length of the circle is exactly 2 pi. Or this hyperbolic geometry where we'll see later what is the metric element there, where the length of the circle is bigger than 2 pi. So Riemann classified, well, he actually didn't prove this theorem. He didn't prove it up to modern standards. He assumed that there is maximizer of some function which wasn't clear at the time. It's like Newton proving ellipticity of orbit, so there was the same mistake. Then what was fixed by Koebe with another mistake. Well, okay, so it was finally done, probably the first correct proof by Osgood. But instead, he indeed classified for all simply connected geometries and non-simply connected, they can be covered by universal cover by one of these three. And you all heard that like 15 years ago, Perelman classified all three-dimensional geometries. So Bill Thurston understood 40 years ago, and he actually came here to Geneva to give lectures about it in 1978, that they could be classified and made the list. Again, the list starts as spherical three-dimensional geometry, where you are on a boundary of three-dimensional sphere, a flat three-dimensional geometry, a hyperbolic three-dimensional geometry, the same guys as here. But for example, in 3 dimensions, you can have the thing which is two-dimensional hyperbolic times one-dimensional flat. It will be different. So there are a few more geometries like that. And at the time, no one believed him. He proved it for one manifold which is three-dimensional space minus figure 8 naught. He proved that it's hyperbolic. And then that was eventually what Perelman did. So the most complicated part there was to do the Poincare conjecture, then the spherical things are spherical. But in the way, he did everything. So it's just an example that this is how important is this theorem. It took 100 years to prove its analog in three-dimensional space, which turned out to be more difficult. Okay, so I think I've seen the statistics that no one has seen the proof. Okay, so Riemann mapping theory. I know some people have seen the proof. Okay, look, I will give later a rigorous proof which you have not seen using some discretizations. But there are a bunch of proofs of it, unlike three-dimensional geometrization, which has only one proof by Perelman. So three-dimensional geometrization works like that. You take any metric on your manifold, and then you run some dynamical system, which is called Ricci flow, which was proposed by Hamilton, which tries to sort of straighten up certain curvature. And then eventually you get in one of the sort of geometries you can have. Unfortunately, on the way, sometimes your manifold collapses. So whenever it collapses, you have to cut it into pieces and do this thing separately. So that was a difficult thing. You can do exactly the same thing here, only it will be much easier. You can write some evolution equation and solve it. Now, what you can do here, you can do optimization without time evolution. That we don't know how to do in 3D. So there are several ways how to write this map phi in one step. Of course, they require a proof. So the idea of a proof, so it's sort of a proof. So let's say take O. Let's say take O psi, which go from omega inside the disk D. Not necessarily maps, just O psi. O smooth. No, let's bet analytic. O psi holomorphic, which go inside D. And which map some specific point Z0 to point 0. Then maximize phi prime of Z0, absolute value. And then the solution will be conformal map, psi prime. So the solution is the map phi. And the reason for that it's sort of intuitively clear, because suppose I have a map and suppose that I put it into disk so that it doesn't cover the whole disk. So if for example, it's inside disk of radius 0.9, then I just multiply by 1.1, it expands, and derivative becomes bigger. So I can make bigger derivative. It turns out that even if it's missing a small part of the disk, derivative can be made bigger. Should I do conformal? Yeah, maybe it's better to say that it's conformal map. Yeah, conformal map inside. Yeah. Conformal map inside. But the difficult points here, so why this is difficult? First, you should prove that there is at least one psi like that. If your domain is bounded, it's very easy. You just shrink it till it fits in the disk. But suppose that your domain is not bound. Suppose your domain is a plane with a slit like this. How do you map it inside the disk? You should write some formula. If I take a straight slit, I can write an exact formula. It's not very difficult. We'll be doing that. But if the slit is curvy, then one should come up with some trick, and Koebe came up with some trick. But also, then you should prove that there is a maximizer. So you have some class of a function. You ask whether there is a function which maximizes this value. So you need to prove some compactness. And then you need to prove that the maximizer is a conformal map. So like a 30-minute task, we can do it at one point, but I would rather do a different proof. There is a proof with minimization. You can take, so this is proved by Koebe, and Osgood. So this is a proof by Koebe. There is another proof. So this is by Bergman, I think. Is that you take O f, which is holomorphic in omega, so that f of omega covers the disk, and then you minimize area integral of gradient f squared. I think it's that, and then it will cover only once, because let me see, did do it correctly? Yeah, I think I did it correctly. Yeah. Did I do it correctly? This is less known. Yeah, maybe. Yeah, I think it should. But basically, that is what is this integral? This integral is exactly the area of the image, and the area of the image will be minimal when you cover exactly the disk and exactly once. If you cover twice, then it counted twice. So it's. So that's it seems a little bit tautological, but there is also a way here to remove the word homomorphic, just minimize around among all functions, and it works. Okay, so we are not going to prove the Riemann uniformization theorem today, but we will give a different proof tomorrow. Well, a different proof not tomorrow, next week. Just before we go to the break, I want to sort of show an open problem. That just already in this area there are wide open problems. So there is a uniformization theorem which says that if you have a domain with a hole, you can always map it to a round annulus. And the question is whether if you have a domain with many holes, can you map it to a domain with round holes? Can you map everything to Swiss cheese? Now, you should be careful that if there are infinitely many holes, for example, Cantor set of holes, then of course some of the images will be not disks because you can have only countably many disks. Some of the images will be points. So can you always map it to a disk minus disks and points? So this is called Koebe conjecture. And the really interesting thing that the best known result is due to that Schramm, whom I mentioned, though it's completely different Schramm part. So Schramm, that Schramm, he did it, yes, for countably many holes. In general, we don't know. We don't know much better than that. It's kind of embarrassing what we can do. You can ask why you cannot do some maximization problem like this. You can. There is a maximization problem which sends everything to straight lines. So there is a maximization problem which will give you a domain which has straight slits in the same direction. So that we can do. But make them round, we don't know. There is no optimization problem. And so what people like Schramm are doing, they're making one component round. Then they're making second one, then the third one. But when you're making third one round, the first one becomes a bit eccentric. So it becomes squeezed. So you have to return and again, and then you have to show that there is a limit. But so there are this is an example, sort of its basic question was posed by Koebe 100-something years ago. It's still wide open. Okay, let's have a break. So as Amanda said, we'll be sometimes composing conformal maps to bring our models to life. And also we need to figure out, I already had harmonic functions, but and harmonic functions, as I said, they play important role in physics. We need to introduce how they relate to some models. So what I'll start with, estimates we will need to do if we to compose conformal maps, because we will need to sort of estimate that it doesn't run haywire when we compose thousands of them. So I will write a few inequalities. So the first one is called Schwarz lemma. It's interesting. It's like there are at least three famous mathematicians who were called Levy and one, maybe two, Hans Levy will be mentioned in this course. So there are several mathematicians who have been called Schwarz, and for example, Laurent Schwarz of the distribution fame. So this is German mathematicians. Some of them are with T, some of them without. So this one is without. Schwarz lemma is the simplest estimate you can write. So what we usually will have homomorphic functions in arbitrary domain. But if I have it in arbitrary domain and I want to estimate in some point, what can I always do? I can do the biggest disk around this point, estimate on this disk. And disk I always can rescale to take size 1. So what it says, so suppose that f is holomorphic in the D. So D is the standard notation for disks once again. And I always can subtract a constant or something. So suppose that f of 0 is equal to 0. So suppose we know that f of disk is inside the disk. So we can always get this. If you have a function which is defined on a small disk and has value somewhere, we can rescale this disk, we can rescale the place where it has value so that it's function from disk to a disk. And then there is a very nice estimate which says that then absolute value of f of z is no more than absolute value of z. Also f prime of 0 absolute value is no more than 1. And equality with equality if and only if f of z is just a rotation of a unit disk, rotation by an angle theta. Let's consider function g of z, which is f of z over z. So I claim that it is holomorphic in the unit disk. Why so? Because when we don't divide by 0, it's clear that it's holomorphic. So for z not 0, it's clear. For z equals 0, it's because f of 0 is equal to 0. So we can factor out, the zeros cancel out, so you get an analytic function. Now, on the boundary of the unit disk, or when you approach the boundary of the unit disk, absolute value of g of z is equal to absolute value of f of z over z. So it's no more than 1, which tends to 1 if z tends to the boundary of unit disk. So by maximum principle, modulus of g is at most 1, which means that modulus of f of z is no more than z. So how you make this rigorous if function is defined only inside the unit disk? So you take disk of radius 0.99, you write this inequality on this disk, and on this disk you get an equality 1 over 0.99, which is approximately 1.01, and then you send 99 to 1, this gets to 1, and you get the inequality. So that's the usual thing. If you have a function defined inside the domain, you can always step epsilon inside. Then the function is not only analytic, but it's also well defined on the boundary. You work there, but then you send this epsilon to 0. Now, derivative is at most 1. It also follows from that. So f prime of 0 is the limit of fz minus f of 0 over z minus 0 when z tends to 0. So it's at most 1. And why, if there is identity, so suppose that f of z0 is equal to z0 in absolute value, then it means that g of z0 is equal to 1 in absolute value. And then by maximum principle, it will mean that it's 1 everywhere. So there are, well, let's say I will do that g of z0 is equal to ei theta. Then it means that g z0 over ei theta is equal to 1. But you always know that g of z over ei theta is always no more than 1. Or real part is no more than 1, for example. So by maximum principle, you get that g of z over ei theta is always identically equal to 1. So this is a very easy lemma, and it uses essentially one fact besides maximum principle, that if a complex function, analytic function has a 0, you can divide by z, and then you still get an analytic function. So it gives you a slightly better estimate. But it has a few corollaries. So one is a corollary which is actually true for harmonic functions in R3 as well. So there it has a different proof. So it's called Harnack's inequality. And it says that suppose that function h is harmonic inside the unit disk, and h is positive there. Then h of z is at most 1 plus r over 1 minus r h of 0, and at least 1 minus r over 1 plus r h of 0, where r is absolute value of z. So basically what it says, so suppose you have a disk and you have this function h, and it has some value at 0, and normally if you have any function, it can behave as it wishes, be very large, very small. Now what happens with the harmonic function? Harmonic function has mean value property. So suppose that this function is very, very, very small here, but it's cannot be much smaller than this, because then mean value property won't be true. Of course, one point won't spoil the mean value property, but this point has mean value property, so around it it's large, so you'll get a contradiction if it's small here. And the other way around, if it's very large here, then you'll get contradiction with it being small. So you can deduce it from mean value property. That's what people do in higher dimensions. And you can also deduce it from the fact, as I said, that here the fundamental solution to the d-bar operator is 1 over z, and the fundamental solution to the delta operator is a logarithm of z, or logarithm 1 over absolute value of z. So you can just say that this is archetypic harmonic function. So harmonic functions can be written as combinations of those. Well, this is harmonic everywhere but 0. So if you want harmonic functions inside some domain, you can take these things with poles outside, and you can always get this harmonic function. So you can prove theorems for these ones, and then you get that. But what we'll do just one step deduction from the Schwarz lemma. And it's neat because it uses also conformal maps. So suppose, let's say f is h plus I h tilde, where which is holomorphic. So we added harmonic conjugate. Now f is a function in a unit disk. Of course, it's not a conformal map. It sends it into the plane, but what we know? We know that the real part is positive. So it sends not just into the plane, it sends into a half plane. And the point 0 is sent to the point h of 0. Let me just do the following thing. Let me maybe, without loss of generality, assume that that h of 0 is equal to 1 just by dividing the thing. So let's say assume h of 0 is equal to 1. It's just the same inequality will be there, but without extra things. Or alternatively, one can take f to be h of z plus ih tilde of z divided by h of 0. Okay, so now you have a function which has values in half plane. Now I want to use Schwarz lemma, so I need values inside the disk. So what is the map which sends half plane to a disk? So this is a small exercise on conformal maps. It's a Möbius map. So any suggestions? So if you have a map of half plane to a disk, it also has a map of a sphere into itself. There are various ways to see it. For example, the one which we'll use later, I don't want to discuss it, but you can say take mirror symmetry here, and for a point which is mirror image of some point, define its image as a mirror image of this point. So here mirror means inversion, here mirror is a usual mirror. So as this is a map, a Möbius map, it can be written as a function of the form az plus b over cz plus d. And now we know that we want point 1 to go to the 0, to the center of the circle. So it has to have z minus 1 in the denominator, so that 1 goes to the center of the circle. And then for symmetry, probably, oops, this is 1. Minus 1 should go to infinity, so it should be z plus 1. So that would do. Actually, that's a good exercise if you have never done it before. Have you distributed exercises yet? No? Okay, you should get from this guy, you should get exercises at the end of the course. So Dmitry is assistant for the course, so he, yeah, okay. He should have distributed exercises, but he did not. So this one exercise, on top of it, just check, if it's not already there, just check that this map indeed maps half plane to a disk. So this, okay. Now, what do we have? We have a map, we have map G of Z. We have composition of these two, which is f of z minus 1 over f of z plus 1. We can use Schwarz. And what we get is g of z over z, absolute value is no more than 1. So it means that, what it means? It means f of z minus 1 absolute value is no more than absolute value of z times absolute value of f of z plus 1. And absolute value of z is r. Absolute value of z is r, so I denote it like that. And now it's just a question of triangle inequalities. So how do you estimate this thing from above? Absolute value of a plus b is no more than absolute value of a plus absolute value of b. So you get no more than r times absolute value of f plus 1. And below, triangle inequality can be written in two forms, absolute value of f minus 1, or you can also write that it's at least 1 minus absolute value of f. So there are two ways to write it down. And the first one, if I move it around, I'll get absolute value of f times 1 minus r is at most 1 plus r. And the second one, if I move it around, I get 1 minus r is at most absolute value of f times 1 plus r. So that's what we need. Exactly. So the first one will give me that absolute. So I get that absolute value of f is at most 1 plus r over 1 minus r, and at least 1 minus r over 1 plus r. Now, from above, obviously, it's okay because absolute value of f is bigger than absolute value of h. From below, what you can always do, look, the harmonic conjugate is defined up to a constant. You can always choose a constant so that at this particular point, harmonic conjugate is 0, and then absolute value of f is equal to h. So it's not a problem. Okay, so that's already a very important estimate, which we will use a couple of times at least, because it says that if you have a positive harmonic function and it's big somewhere near this point, it will be big. It can be very big, it cannot be small. So it's and it's applicable to any domain. So if I have some domain and I have positive harmonic function there, for any point there is a ball around, so I can always work inside this ball. And if I want having estimate for this point, I want to get estimate for that point. What I do sequence of overlapping balls, and from here I get estimate here, from here I get there, from here there, and eventually I get some estimate here. So it basically says that whenever you have 2 points, you can sort of connect them by this kind of whatever sausage-like structure, this bunch of beads. Then you get estimate, but each time when you attach another bead, you use a factor, so the estimate gets worse and worse. Okay, now there are even better estimates on conformal maps, so it's called distortion theory, and it was started by German mathematician Koebe. So it's Koebe distortion theory. So the same principle is that we want to do it in arbitrary domain. But what we can do with arbitrary domain, we can always map it to a disk and work in a disk. Or we can always surround our point by a disk and work in this disk. So Koebe distortion, you normally formulate theorems for functions on a disk, and then you make versions for arbitrary domains which are not as precise, but usually up to a constant is enough. So we usually reduce everything to conformal maps, conformal in D or in D minus. So D minus is a complex sphere minus unit disk. So sometimes it's convenient to play with functions which map unit disk somewhere. Sometimes it's convenient to play with functions which map outside of unit disk to outside of something and preserve infinity. So these 2 classes are functions f of z, which can be written, okay, if it's a map of unit disk, you can always subtract a constant so that 0 is mapped to 0. And you can always divide by a number so the derivative is 1. So you study functions which look like z plus a2z squared plus a3z cubed and so on. And another class in D minus, it's functions g of z. So they look at infinity like z plus b1 over z plus b2 over z squared plus so on. And these classes are both denoted by the letter S for German Schlicht. So this one is denoted class S, usually in brackets, and this class sigma in brackets. So they're both called classes of Schlicht functions. They call Riemann, Koebe, Schwarz, so that at that time powerhouse of conformal maps was in Germany. So it's like Göttingen, Berlin, Hamburg. Okay, now there is so it's not the approach which Koebe did first. It's one which Gronow did a little bit later. So it was called Gronow area theorem. And it says that area of f of the unit disk can be written in terms of coefficients. And it's a sum, it's pi times sum of n absolute value of a n squared, n from 1 to infinity. So the first coefficient in 1, and then the rest. Now, I cannot write area of GD minus because area of the image here is infinite because it contains infinity. But I can write complement of the area. So area of the sphere minus the image. So it's basically in the first case we do the area of this domain. In the second case we do the area of the complement to our domain because both are finite. Bless you. And the second one is pi times 1 minus a similar sum for k equal 1 to infinity kb squared. So the first one is easier to prove, but we need the second one. So I will prove the second one for that reason. So the first one is just the same, but easier. So first one can just write, the first one you can just write integral of f prime squared over the unit disk. And then you write it in terms of its integral of f prime times f prime bar over the unit disk. You plug in the series, and you just do the calculations. The second one, we cannot do that because we are not taking an image. We do the area of the complement of the image. So we do the tricky thing. First of all, we map outside of a unit disk to the outside of some crazy set. So I draw, of course, a nice set, but in reality it might be a fractal. It might be like a Julia set or a von Koch snowflake or anything, one of these diffusion fronts. So you cannot really define f prime on the boundary of this set. So to circumvent this, we step epsilon away, as I said. So it's the same. We use the same trick. We step epsilon away. And then here, of course, we had a rough set. Let me just possibly just say that it might be rough. But when we step epsilon away, it becomes very smooth. Well, maybe not very smooth, but it becomes smooth, infinity smooth. Now, how do I calculate the area? I take some vector z, and I take a small triangle, and then I take next triangle, next triangle, next triangle, and there is the sum of these triangles. So we go back to Archimedes with some triangles, and then descend the base of triangle to 0. So we take here a triangle. So if this vector was z, this vector is I epsilon z. So it's rotated by 90 degrees. Now, what happens here? So again, so this is point 0. So we have a vector, let's say, so this is function, what is it, g of z. And then the vector will be, maybe just this vector is g of z. This vector is, I should just map this small thing by map g, which is conformal. And remember, I live on a nice smooth curve. Yeah, maybe so it will be multiplied by g prime. So this is approximate vector. And what I do, I just need to add areas of all these triangles. And I get my area. Now notice the tricky thing. For example, when here I go to the right, my triangles overlap. But the triangle which goes to the right, which goes clockwise, is counted with the sign minus. So you cover, so you should note that this is plus area. This is plus area. But the next triangle, if it goes like that, it's counted with the sign minus. So this doubling carry, it cancels out. So what happens, for example, for if I have a nice curve like that, is that I go and count all these triangles with sign plus. But then when I go in the opposite side, I count these triangles with sign minus, and this is cancelled out, so I get only area of my guy. So this is perfectly legitimate. So what happens is that on the left, if I integrate it, it's so yeah, maybe I would just write it here, that here it's to the left the area. What is the area of this triangle? Side 1, side epsilon, and there it's orthogonal. So the area is epsilon over 2 approximately. Now here the area is approximately, well, again you will get epsilon and you will get over 2, but then what I claim is that it's a real part of g of z times z bar g prime of z bar. So this is kind of, I don't know, exercise, not exercise. So if I have a triangle which is formed by two vectors p and iq, so those are the two vectors, then what I claim is that the area of the triangle, what's the good for triangle, so it will be 1/2 of the PQ scalar product. Why? Because scalar product has cosine of angle between the vectors, and I have area. Area has the sine of angle between vectors, but here there was rotation by 90 degrees, so sine becomes cosine. That's because, well, there is this careful I there. And this is, in terms of complex analysis, is exactly 1/2 of the real part. So if p and q are complex number, p times q bar. Or, well, yeah. Or equivalently, it's 1/4 pq bar plus p bar q. So this is an exercise in complex analysis to check that the scalar product of two vectors is given by p times q bar. Real part p plus times q bar. Okay. So now what we get? We get that we are in business. So the area of the sphere minus g of d minus, we should just integrate this thing. So we integrate it with respect to, well, the circle has length 2 pi, so that we should remember integral from 0 to 2 pi, 1/2 real part, and the real part is of what? Of g times z bar times g bar prime. Okay, so it's integral from 0 to 2 pi, 1/2 real part. Now for g, I plug in the series z plus sum of bk over zk. And for the other part, I take z bar times the derivative of this series. So z derivative is 1. Bk over zk derivative is k bk over zk plus 1. And again, complex conjugate. Now the first series I leave as is. And the second one I put z bar under the thing, so it's z bar plus sum of k bk over z bar to the power k. So we basically have two identical series, one with bar and also with k. And now there is a very nice observation. So if I write integral from 0 to 2 pi of z to some power, let's say, n times divided z to the power n times z bar to the power m, what is the result? Well, on the unit circle, z bar is equal to 1 over z, so it's integral from 0 to 2 pi z to the power n minus m, which is equal to 0 if n is not equal to m, and which is equal to 2 pi if n is equal to m. Because if n is equal to m, you integrate constant 1. If n is not equal to m, you integrate z, which will oscillate. It's like sine, cosine, it's plus, minus, it will cancel out. So when I take one term from here and one term from here, the integral will cancel out unless I take the same term with the same number k. So the conclusion is that it's 0 to 2 pi integral of 1/2, and then I get only terms where you do the corresponding things. So it's real part 1 plus sum, and the sum will be, yeah, bk was with bar, k, bk absolute value squared, let me see where I confused everything. When I was differentiating, there should be minus sign because I was differentiating 1 over zk, so derivative is 1 over zk plus 1 with minus sign. Yeah. And then the integral will be 2 pi, so I just put 2 pi here, 2 pi over 2, and that's it. Well, 2 can be cancelled out. Now there is an immediate corollary of this fact. And the immediate corollary is that area is always positive, not negative. So area is non-negative, which implies that 1 is at least sum of k bk squared, which implies that b1 squared is at most 1, or rather b1 is at most 1. And that's the estimate which apparently can be used to estimate many things about conformal maps. So this looks a little bit like cheating, in the sense that the area calculations, they are, the first part is even easier, the second we have to do this trick, but then we get a result which is always positive number, which means that 1 is always bigger than this guy, which means that b1 is almost at most 1. And now I will use it to deduce one distortion estimate, and I don't think I will do others, I will just point how to do them. So it's the famous Koebe theorem, and okay, let me just see. Yeah, so it's Koebe 1/4 theorem. So if f is in this class S, then image of the unit disk contains 1/4 of the unit disk. So the immediate remark is that if you have f, which is conformal, or rather let's say phi, in the domain omega, and then there is a disk of radius r here, then in the image should contain which disk? So we need to reduce to the first case. So when we reduce to first case, first we shrink or stretch to get this, so the area here should be at least r, and also we change derivative to 1, so it's at least r f prime of z0 and 1/4. So any conformal map of any domain, if domain has around z0 a disk of radius r, the image will have disk of radius 1/4 r times f prime. So you can, if we would prove it without 1/4, it would mean that just basically our map, like a linear map, it just linear map would have had a disk exactly radius r times f prime. But conformal map, it turns out, is not that far from linear. It's globally different from linear only by a factor of 1/4. So this is a very strong theorem. So this is also, it's always formulated, or not always, but often formulated, is that distance from f of z0 to the boundary of f of omega and distance from z0 and boundary of omega. So their ratio is at most for f prime and at least 1/4 of f prime. So distances to the boundary are changed by at most factor of 4. So it can drop by a factor of 4, it can increase by a factor of 4. Okay, now the third remark, that this estimate is sharp. There is a function which is k of z, which is called Koebe function, which has the very nice formula sum of n z to the power n from 1 to infinity. And this function, it actually maps unit disk to a plane with a slit from minus infinity to minus 1/4. So it exactly gives you minus 1/4 thing. And you can, well, it's an easy exercise. You can write a closed formula. It's like, you know, twice, if you just have this, it's like summing a geometric progression. Everyone knows this. And this is summing geometric progression twice. So summing derivative of geometric progression. So I always forget what the formula is. Probably it's z over 1 minus z squared. So if I plug in -1, I get minus 1/4. If I plug in 1, I should get infinity. Yeah, that's it. Okay. Now, okay. So now, how to prove the Koebe's theorem using this coefficient? Well, to start with, I have a map of a disk, but I can use theorem about the complement of a disk. Let's do a small trick. So suppose point C does not belong to the image. Take G of Z equal to f of Z divided by C minus f of Z. Yeah, C f of Z, C minus f of Z. Oh, I forgot one small thing. Yeah, okay. I forgot one small thing to do. I just accidentally skipped over. We'll do another inequality which says A2 is no more than 2. Yeah. G of Z is C f of Z over C minus f of Z. And you can expand it. So if you can expand it in terms of f. So if f of z is z plus a2 z squared plus so on. So when you expand this, it will be z plus a2 plus 1 over c z squared plus small order terms. It will be in the Schlicht class because it's in this form. If it's in the Schlicht class, then the second coefficient is no more than 2. I am sorry, I forgot because I mentioned it on the slides, but yeah, okay, so it's just in 5 minutes we'll do this thing. So a2 plus 1 over c is at most 2. So by triangle inequality, it means that 1 over c is at most 2 plus absolute value of a2 is at most 4. Which means that absolute value of c is at least 1/4. And we are done. Now, so this is, so why A2 is no more than 2. So this is called Bieberbach theorem. A2 is no more than 2. The proof goes like that. So the proof reduces to this area case. So f of z is in the class S. So f of z squared is not only a holomorphic function, it's also an even holomorphic function, because this has the same values at z and minus z. Which means that you can take a square root of it, and it will be holomorphic. And also in class S one can check. One can do 1 over square root of f of z squared, and it will be in the class sigma. One over, let me see, 1 over, well, yeah, like that. And here I don't have the time to do it. So Bieberbach did it 100 years ago. So if you have expansion for f of z, sum of ak, well, sum of well, z plus a2z squared plus so on, you can plug in this expansion here. And you can trust me that if you plug in this expansion here and you take the square root and everything, you get that this whole thing gets expanded as z minus a2 over 2 1 over z plus small over the terms. So this is a calculation which is not very difficult to do. So this is then coefficient b1. So this is coefficient b1. So absolute value of a2 over 2 is absolute value of b1. It should be no more than 1. So a2 is no more than 2. Okay, so I should finish here. Do we need derivative estimates? No, not really.
I can do them if I want.
Yeah, we will do them when we need them then. So I will just, instead of doing, so this tells you how distance to the boundary is perturbed. So I will just write a few corollaries of this, which are basically the corollaries of this estimate. So I don't think we need to prove them, but it's just, so there are a few corollaries which are done by various integrations. So it basically says that if f of z is in the Schlicht class, so it's in the unit disk, it tells you that f of z, absolute value of f of z belongs to, well, let's say absolute value of z is r, belongs to r over 1 plus r squared, r over 1 minus r squared. It's very much like Harnack's inequality. Here it's done by integrating this 1/4 type statements. And f prime of z is in between r over 1 plus r cube, r over 1 minus r cube. And there are a bunch of other estimates. You can also do estimates on rotation, on different like Schwarz type derivatives. So it just basically says that of course conformal map is not linear, but if you have a disk, inside the disk, in very small disk it's linear, almost linear. But when the disk grows, you still get an estimate how far it is from linear. And the one which is easy to remember is 1/4. Usually 1/4 is enough. Okay. So now I will just finish up with two open questions. And one was open till, well, maybe one open question. Yeah, it's enough. So Bieberbach did A2 no more than 2. So what Loewner did using Loewner evolution, Loewner did in 1928 A3 no more than 3. And what took many years, and it for a very long time it was kind of proposed as the main subject of complex analysis. Prove that an is no more than n, because that was the conjecture, the original conjecture that this function is extremal. So that was done finally by de Branche, American mathematician of French origin, in 1985. So he did that an is no more than n. Before, people did many other things. So it's the easy proof which we could do today. It's very easy to prove that. Well, you shouldn't say very easy. It was done by Littlewood, but it's easy to show that an is no more than en. That was done by Littlewood, and that was not very well. It's very short. But that took indeed 60 years, and it was big thing for a long time. If you do the very same thing about what is Bn for the class sigma, that no one knows. So Bn, so suppose that, let's say, take best gamma, so that Bn is no more than n to the power gamma minus 1. So the best thing which we know today, so we only know is that gamma is at most 0.48, and that's Hedenmalm and Shimorin in Stockholm, and at least 0.24. That's my student who is now in Oxford and myself. And that's really mysterious, because here the growth rate was done by Littlewood with constant t long ago, and here it's very widely open. Now, why do I mention it? First, well, it's nice to have a wide open conjecture, but second, it relates to the subject of this course, because it turns out that here the extremal example for class S is this nice plane with a slit. Here it turns out the extremal example is the fractal domain, which we don't know. So here the worst gamma is the same gamma as that if you take your domain and you draw the green lines. So we will discuss them in a week. So you draw electrostatic equipotential of potential delta. And you suppose that its length of this gamma delta is at most 1 over delta to the power gamma. So that's the same gamma. That's the same gamma. So the question here is why we don't know, because we don't know what kind of fractals, like the ones Amanda mentioned, like these crystal things, they have the longest equipotential. It also relates to some physically important question. For example, if you want to make the best electrode for your car battery, it should be fractal which maximizes this gamma. Of course, it would be very. There are actually people who are working it for Formula 1 or space shuttles, but then, of course, they become very difficult to produce this and very expensive. So people just stopped at some sort of approximation. Okay, but that's an example of open problem and complex analysis. Okay, so next time we'll do some harmonic measures, some potential theory, and explain how it relates to physics, and then we'll start doing some background in probability, I think. Okay, yeah. Am I going too fast? It will be slightly different when we skip, because it's kind of things which you should know to follow the course, but you should not really know all the proofs. If you think we should go slower, please feel free to apply the brakes. You can go someplace. You can also come walk in, ask questions, so you can. Yeah, ask questions during the recitation section, or, yeah. Okay, thank you. Have a nice. Yes.
We will always have 3 hours of class.
No. Well, not always. Not tomorrow, for example. But I think we'll have 2 hours of class and 1 hour of exercises. And Dima, who has fallen asleep at the last desk, you should have been following. he can give you exercises when you exit. So usually we'll have 2 hours of class and 1 hour of exercise. No, otherwise, we decided that the first hour wasn't really to a class. We're just showing pictures. It's kind, yeah, not a real class. So it's so to say.